Hey, welcome back to Math with Patrick. Today is February 11th, and we're solving problem number 42 from this Daily Epsilon calendar. Okay, let's try this out together. How many ways can one partition 6? Okay, let's talk about the word partition for a sec. This just kind of means split into pieces. Usually when you see this word used in math, it's to partition a number based on place value. So like the number 16, you can partition it into 10 and 6. So it's a little bit easier to see that it's made out of, well, a 10 and a 6. If we did this for a higher number, like 7,816, usually the way that partitioning works is that you split it into its thousands, its hundreds, and then tens, and finally ones. Now, this question is a little weird because when I'm just dealing with the number 6, there is no like place value to worry about. 6 is just, 6 objects. It's such a small number that I could just represent it by a tally, and it wasn't that hard to just tally them all out. It's kind of the basis of why we count in base 10, because it'd be a little silly to write out 26 tick marks. So eventually you just got to be a little bit more concise with the way that you write your numbers. But the number 6, it's so small, you could just see all 6 objects. My guess here is that it's asking us how many different ways can we split up 6 things into different groups. And not just 2 groups, but maybe I could do like 3 groups like this. Or maybe I could do 3 groups of unequal size. Maybe I could do 3 groups where 2 of them have the same size and the other one's different. So I think that's the goal for this question, is to count up all the different ways you can organize 6 things into different groups. And as we figure out different ways to partition 6, let's just tally them up. So let's see. I think there's 2 obvious ends to this spectrum. I could grab all of them, and I'll put a little, how about all down here? That's way number 1. I could just put all 6 things in one group. I didn't partition it at all, which technically is a partition. And the other obvious one to me is just putting each individual one in a group. And maybe I'll call that the lonely partition, because none of them have a pair. Okay, so I've already found 2 ways to partition 6. I grab them all, and I grab them all one by one. I think it might be easiest for me to try to count bottom up. So like starting with the idea of grabbing them one by one, I want to think like, what's the next smallest way I could grab them? And I think the next smallest way would just be to shove 2 of them in one group together and keep the other 4 alone. So maybe I'll call this one couple. And I'm pretty sure this is indistinct from putting these 2 together, as in like grabbing a couple in the middle isn't really functionally any different from grabbing a couple on the side. So I don't think this creates a new partition. Okay, so I did the lonely partition. I did the one couple partition. Yeah, maybe I guess I'll count up by only using ones, then only using ones and twos. I was wondering like which way I should thematically or systematically count this. I was wondering if the next best one would be to do a 3, 1, 1, 1. I think it's best if I limit my range from low to high. Just this way I can keep in mind how I'm counting my 6 things. So got the lonely partition, got the one couple partition. So let's do a 2 couple partition. Maybe we can call this a double date. Double date. Okay. And then the only other way I can count with groups of 1 or 2, I believe, would just be to shove these 2 together in another group. So let's call that a triple date. Okay. So I think that's all the ways that I can make groups of size 1 or 2. Now let's work on groups of size 1, 2, and 3. And well, I've already covered all the cases of groups with 1 and 2 and no other numbers. So all of my other ones that I'm going to add to this list must have a group of 3. So I think the obvious one is to grab a group of 3 here, keep the other one separate. Maybe we'll call that one triplet. Then what else could I do? I guess then I could have a triplet and a couple. That's another way. So triplet plus couple. And I could have also had a triplet plus a triplet. So that's another way to partition 6. So triplet squared, because I have 2 of them. Okay, have I counted all the ways to include exactly, or like, yeah, I think I have all the different ways to partition 6 using only 1s, 2s, or 3s. I hope I didn't miss any. So I guess now I could move on to the 4s. So I could grab a group of 4, keep the 2 on their own. So let's say 1 quad. And then my other alternative was to keep that quad there, but then group the pair together. So I'll call this, I don't know, 1 quad, 1 couple. I guess I was being all cute with my names here with like double date or whatever, but I couldn't really think of anything off the top of my head. So 1 quad, 1 double. And there's no way for me to make a group of 4 and another group of 3. So I shouldn't, or I don't need to consider that. Onwards to 5. So I could grab the whole group of 5, and that's it. Because then this one is kind of stuck to be in its own lone group. So then the group of 5, I'll say odd one out, because this one, odd one out. This one is all about this last guy not being in a group. Okay, I hope that was 11, or else I might have missed one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Nice. I'm so good at counting. All right, that's all the ways to partition 6. I guess my recommendation here is to create some kind of systematic way to count either low to high. Maybe high to low would have also worked. Either way, you can make sure that you've counted all the different ways to partition 6 things. Was that a 1 take? Nice. All right. See you tomorrow. Thanks for coming along for this one. Bye. Or you could stick around. I have a question. Is this generalizable? What a mathy question to ask. As in, how many ways could you partition 5 or 4 or 3 or 2 or a million? Okay, maybe not a million. I might be like getting ahead of myself there. But there should be some kind of pattern here. Like, it should grow. Obviously, there's more ways to partition 7 than 6. But I want to figure out, like, how many ways can I partition 28? I'd rather not have to go through that whole list like the systematic counting way. I'd rather have some kind of function where I could just input the number 28 and get the number of ways I can partition it. I have an idea. I really don't know if it's going to work, but maybe I could do this recursively. Let's try it out. So how many ways can one partition 1? Here, I'll do, how about x for the number I'm trying to partition, and then p of x is going to be the number of ways to partition it. So if I have actually, let's start with 0. How many ways can I split up 0 things? Usually with counting problems, when you have like the empty set or like the ability to do nothing, that does count as something. So I think it should be a 1, because if I have no objects, I can just sit there and do nothing. And I think that's a valid response. Okay. How many ways can I partition a 1? Well, I could only just put it in a group. I have no leeway here. I have to put stuff in groups, and once I put the 1 in a group, well, that's the only way for me to do it. When I have 2 objects, that finally gets a little bit interesting. I could either keep them alone, or I could put them together. That's it. And when I have 3 things, I could keep them all alone, put them in a pair. So I keep them all alone, put them in a pair, and 1 alone, and then put all 3 together. So far, nothing really interesting is happening with this pattern. It just looks like I'm counting 1, 2, 3, 1, 2, 3. Okay, onward to 4. I guess 5, 6. We already counted that up. That's 11. how many ways can I partition 4 things? I could keep them all alone. That's 1. I could put this in a pair. I could put that in a pair. I could put 3 in a 1. Or I could do all of them. And then let's try a 5. So I could keep them all separate. I could do 1 pair. I could do 2 pairs. I could do a 3, 1, 1. I could do a 3 and a 2. I could do a 4 and a 1. And then I could do all 5. 7. Okay. I do notice something going on in this table. I'm not quite sure about it yet, but I do notice that if you start at least here, you can double your number and then add 1 and get, well, 1 times 2 is 2, plus 1 is 3. But that works for all of these. You could double and add 1 there. You can double and add 1 here. You can double and add 1 there. So maybe the pattern persists. 7 doubled is 14. Add a 1 is 15. And then you could perhaps do the same thing to that 11. And so here's something that I want to try to prove or disprove. Is this actually the case? Okay, maybe I should count out the 17 just to see if this pattern works or not. Did I say 17? I meant 7. 1, 2, 3, 4, 5, 6, 7. Let's do this quickly. So I could do all alone. I could do 1 pair. I could do 2 pairs. I could do 3 pairs. That's it. I could do a triplet. I could do a triplet in 1 pair, a triplet in 2 pairs. I could do 2 triplets. Okay, and I think that was all my ways of doing it with 1, 2s, and 3s. So let me grab a 4. So 4 and alone, 4 and a pair, 4 and a triplet. That's all. I can do 5 and nothing else, 5 and a pair. Then I can do 6 and then 7. 5, 10, 15. I don't know why I counted my 5 like this, but it's 15. It's following this pattern. That is very peculiar. Okay. The next number I predicted was 23, but I have some bad news. So we're actually just finding something that's already been found. This is called the partition function. And unfortunately, the next number was 22. So if we partitioned 8 objects, we would have gotten 22 distinct partitions instead of 23. So that times 2 plus 1 pattern that I thought I found breaks right here because you go times 2, not plus a 1. 15, you go times 2, not plus a 1. And then this pattern breaks down even further later. Double of 22 is going to be more than 42. So unfortunately, this pattern doesn't persist. Let this be a lesson. If you think you found a pattern, double check. It might not keep going the way you expect it to. So the way that I found this was I just typed in the first few numbers that I found. Usually when you're studying a list of integers, you're going to find that exact list of integers on the OEIS, the Online Encyclopedia of Integer Sequences. And here we can see that this is a well-studied pattern. It goes on and on and on and on. So today's date is the 11th, and we figured out that you can partition 6 in 11 ways. And there isn't a nice and easy way to continue this pattern. But there's a hard way to generate these numbers. They have something to do with the pentagonal numbers, which start with 1, 2, 5, 7, 12, and so on. There's apparently a way to generate them, which is given by this function here. And once you know the pentagonal numbers, it gives you some kind of pattern to make a recurrence relationship. Kind of what I was trying to do, where I looked back at previous values to help me find the next one. It says that so P of n, looks like they're using a similar notation to what I did. I just wrote a capital P instead. Whoops. If you're trying to find the number of partitions for a number n, it's equal to the previous 2 numbers added together, but then you subtract a little bit from before. And then my guess is that it's a plus plus minus minus plus plus pattern. I'm looking up here how it's like minus minus plus plus minus minus plus plus. So my guess is that to find P of n, you'd add these 2, subtract these 2, and then the next numbers you'd add would be P of n minus 12, and then add P of n minus 15 here. And the bigger your number n, the more of these plus plus and minus minuses you'd have to do. So this pattern gets really, really complicated for bigger values of n. However, someone out there, maybe many people out there, figured out that you can actually generate these numbers using some kind of recursive relationship. So I figured I'd share that. It's kind of beyond my scope, to be honest, but I'm glad that I'm able to find that pattern online. And I'm happy to know that there is a way to generate these numbers for very large values of n, but not something that I want to do by hand. Okay, thanks for coming along. It was great doing this exploration at the end. And I'll see you tomorrow. All right, bye.